Welcome to Study Loop.
So let's just begin solving problem 22. First of all, let's just set it up. So we have parallel rays passing through two slits. The wavelength of the light is lambda equals 500 nanometers. And the distance between our slit to the screen, we call that x, it equals 90 centimeters. We don't know the slit width A here. We don't know, and we also don't know separation between the two slits, which is called D. D. Also, we don't know. What we learn is the rays pass through those slits, and they will form some pattern there. Basically, those patterns are the diffraction patterns combined with the interference patterns. So if they're, or say if they are just interference, what we may have is this. This is the intensity of light. But if we just have the diffraction, or say if there are just one single slit there instead of two slits, what do we have? Maybe is approximately something like this. Okay, now if we have both, what will happen? In this case, slit width A is comparable with the separation D. They are almost at the same level of the quantity. So the final result of the pattern will be something like this. Something like this. It looks like just like the interference pattern was confined by the green curve, was confined by the diffraction pattern. So that's the basic physics of this. From the problem itself, we learned that the bright pattern distance between I mean the peak from here to here. It's our y here. It's our y. It's 1 centimeters. Okay, let's write it down here. So now this is set up with this problem. Okay, let's just go back and try to initialize every variables, and now we begin to apply the equations we learned from this chapter and the previous chapter about the interference, and then get the calculation. So the problem side, the third brightness band is missing on both sides. So which means the third bright band is missing because of the first order single slit minimum occurs at the same angle as the third order double slit maximum. So from the equation 36.8, we learned that we have A, the slit width A times sine theta. It equals m times lambda. And from the equation in chapter 35 about the interference, we learned that the separation d times sine theta equals capital M times lambda. So in our case, we have same lambda, and at the same angle, this is the dark minimum occurs, and this position is the brightness maximum occurred. If they happen on it the same angle theta, the brightness will be eliminated by our diffraction effect. So basically they have same angle theta here. And we learned that the third brightness band is missing, which means M equals 3, the capital M, and our order of the diffraction, this is the first, because this is the first dark fringes have occurred. So M equals 1 here. So basically what we learn, we can evaluate is the relation between our A and D here. So we just combined those two equations together. We can get that A equals D over 3 here. Okay, that's a relation. That's a relation between the separation and the slit width. And for another quantity theta, how can we calculate the theta here? Remember that theta is actually just the angle decided by the position of our dark fringes and the distance between the screen and our slit x. Let's start y there. So we can learn that the tangent theta equals delta y over x. It's approximately equals sine theta equals 0.0111. The unit is meters. So now we can directly calculate that about the A and our D here. We just simply plug in the sine theta, the value of sine theta, to our equation here. And A equals lambda over sine theta is about 1.5 times 10 to minus 5 meters. So D, according to this relation, so D is approximately 4.5 times 10 to minus 5 meters. Okay, that's all for this problem. Thank you.